Okay, let's cover beam deflections next. So I'll cover here, I'll just kind of outline the process for you in this slide. And a lot of these images are taken from Beer and Johnson, a book that covers mechanics and materials. But really what it comes down to is, that, this equation here. We know this equation here, this one right there. So you can integrate that equation a couple of times. And if you do that, you basically get this formula, right? So if you know that moment equals EI y double prime, you can integrate these twice and integrate these twice. And when you do that, you get this equation there. And hopefully that's clear, that that's what you get. And so really the strategy there then is to, just use that formula. Just use this formula with you have two constants that are unknown. You have different boundary conditions. So for example, the top one is simply supported, where at point A and point B cannot vertically deflect. In the next one down is overhang, but the same situation. Why the deflection at point A is also 0, but point B is also 0. And then the one on the very bottom is a cantilever beam where the slope and deflections are 0. And with those alone, with these two boundary conditions, it's possible to solve for C1 and C2 very quickly, which means you know the deflection of the beam, number one. But if you know the deflection of the beam, you know the moment across the beam. So very simple process. I'll just do some examples coming up. No worries. We'll get there. If you had a distributed load requires you to use this equation right here. The negative sign that you see there is because W now is pointing downwards, where all my derivations, the pressure load was shown upwards. Anytime you have any doubt, this is what I suggest. If you have doubts about the sign convention, which even my TA and I were confused for one of the problems, you know what we did? We're both confused. We ask ourselves, okay, let's just solve something simple that we know the answer. Because everybody agrees. If I apply a load to a beam that's downwards, do you expect the beam to go up? Right? Does anybody expect? I mean, that'll be cool. If you can invent a machine where you apply the load downwards and the beam deflects upwards, that'll be cool. You're creating energy. That's an amazing thing. Let me know so I can take your patent and make money. But we know that that is not the case. We know that if you apply a load downwards, the beam should deflect downwards. So why not just do a simple problem if you're confused and make sure that that actually occurs? And if it doesn't occur, you know you got the sign wrong. Okay, that's one way to figure it out. The other way is to look at first principles, the way I did in today's class. And if you did that, then I think things will make sense to you. But that's why the negative sign is there, is because in my previous derivation, W, the pressure load applied to the beam, was pointed upwards. So you'll start with this equation. If you have a distributed force like that, you'll integrate that equation 4 times, which you can see here, that's integration over, integrate once, twice, 3, 4 times, okay? Very simple process there. And that gives you 4 constants now, and you have to determine those constants from the boundary conditions. You have nothing else other than boundary conditions that need to be used. And in this case, in this instance, you'll have to now recur to the fact that on this end, there's no shear load, there's no bending moment applied. And you're gonna have to start looking at additional boundary conditions that are beyond kinematic constraints. For example, in the simply supported case, you have no bending moment on this end and no bending moment on this end. So you can apply those boundary conditions as well. While if you didn't have the distributed force, you could just use the deflections and you're done. I mean, you can just use these deflections and you can just get the constants and you know how the beam deflected. But the minute you have this extra distributed load, you're forced to also examine boundary conditions beyond deflections, like moments applied and shear. And here, clearly, we don't have any bending moments or shear applied. So, yeah, so the other kind of problems that you may encounter are statically indeterminate beams. Statically indeterminate beams are all the examples I'm showing here. Number 1, that's one example. And in that example, I have a cantilever beam on the left-hand side and it's pinned on the right-hand side. If you look here very carefully, you will see that you have multiple boundary conditions, multiple reaction forces, and then these equilibrium equations are not enough to solve the problem because you have more unknowns than equations, and so you're kind of stuck. So problems like that, what you want to do is to do this very similar integration, which will produce two unknown, but you have three equations. And what you'll do is you'll enforce those boundary conditions, and I'll give an example on how to do that to solve those kinds of problems. So why we don't step to problem number one, because I think that's one of the best ways to learn is through example problem. I covered the theory. Am I asking you to become Euler-Bernoulli beam in the 1750s and derive the equations again? I did not ask you to do that. Did I ask you to at least understand where it comes from? Yes, I did. That's okay. Learn where it comes from, and then apply. In this case, you're learning how to apply. You're learning how to apply, and then that's all I want from you. But if you do become a professor, if you decide that you want to teach this, then it is required from you to learn the derivation because you'll have to teach it to somebody. And that's an important aspect of teaching. So it depends what you want to do with it. The application is okay with me. I apologize. I have a beam applied with an applied load P with a pin support on the left and a rotor at point B, which means it cannot deflect at points A and B. And the question that is being asked here is to derive the equation for this elastic curve. And you can determine the maximum deflection too, but we may not do that. That's a very easy thing to do. Once you have the deflection of the curve, all you have to do is figure out where it's deflecting the most. It's not a very difficult thing to do. So the solution that we're going to use is to develop an expression for the moment first. And then we'll use the moment as an approach to solving for the deflection. We'll integrate that moment equation twice to get constants, and then we'll apply the boundary conditions to solve the problem. So let me step through the process. Here, what you see is what I've done. I've removed the reaction forces at point A and point B, and I replace them with a force that's going, you can put it in any direction. If you don't know which way it's going, that's fine. When you do the moment calculation, about, in this case, it was taken about a point, a particular point, you will see that in this case, the sign convention you use doesn't matter. So you can make RA going upwards or downwards. It'll correct it for you, because if you take it upwards, it will give you a negative of what I got in this application. But the idea here is you're going to take the supports, replace them by these reaction forces, as you can see in this picture. And what I'll do next is to get the reaction forces by summing, you can sum forces, some moments about C. You can do that. You can also sum forces in the y direction. And when you do that, you get the reaction forces is P times A divided by L, which is the value for the left reaction force. And the reaction force at the rotor support is RB equals P times 1 plus A over L. This is covered in a different class, in a more basic class, which is the reason I'm not going to those exact derivations at the moment. I do want to step into what we came here for, which is once you know these reaction forces, that's the new part. Once you know these reaction forces, and you know it is P times A over L going downwards at point A, what you will do a cut in the beam somewhere. In this case, I've made a cut randomly at a distance X from the left-hand side. And what I did now is that I know that at that cut, there'll be internal forces reacting external loads, just like stresses are. Stresses are free body diagrams that we can extract out of the cube that represent forces that develop inside the structure that react external forces. So if I do that, I have a moment on that point D and a shear force pointed downwards, shear force V. And so what I do then next is I will calculate the moment. And that moment is very easy to do. If I take some moments about this point A, the beautiful thing is that that reaction force goes away. Actually, I did it about point D, now that I think about it. I did it about this point D. So that gives me P times A over L times X. And that's that moment there between 0 and L. So between these 2 points, A and B. And so now that I know that the moment is that much, I plug that in here, recalling that moment is also equal to EI Y double prime. We derived that equation earlier. And so all I have to do now is integrate that equation twice, and I'll get the 2 constants that I need. Any question at this point in time, is it straightforward, or are there some confusion? Is it straightforward? But now what I'll do, I'll integrate it twice, and that's what I did here. I integrate it once to get this, then integrate it again to get this. 2 constants. And how do I solve for those 2 constants, C1 and C2? How do I find them? Yeah, boundary conditions, 20 points. And how do I find the boundary conditions? I have them. At y equals 0 is 0. At y equals L is how much? And how many equations I have? One, I have this equation. I can write that, right? To get C1 and C2. 2 equations, 2 unknowns. True? And I did it here. The rest is math. I won't bore you with the math, but this is the deflection of the beam once you do it. And I invite you to try it at home, step by step, or pause the video and kind of do it slowly at home. You know, the intent here is not to teach you math, but it's to teach you the steps that are taken to apply to the problem. Now, I do want to discuss that we did have a tutorial on how to use Mathematica, for example, wolframalpha.com. So for those that did not attend the discussion session, that's one of the things that was done, and I think that will benefit you in the future. Now for the final, obviously. Any questions you have on this particular problem? How do I find the max deflection of the beam now? I take the derivative of y respect to x, set that equal to 0, and then figure out what location of x that happens. Do you think that the maximum derivative will always mean there's a maximum? It could be a minimum too, so be careful. There might be more than one point where you get a maximum, this slope being 0. Okay, with that said, I think we covered that example very well, and we can move on to example number 2, where I have a more complicated problem here where it's indeterminate. This beam is indeterminate in the sense that I have equations, I have unknowns, but I don't have the same number of unknowns than equations, and so I'm kind of stuck. And so here, what we've done here is showing you a triangular load distribution. I'm showing you a roller support on the left-hand side, but it's also clamped on the right-hand side. If this support was not here, then you get just a regular problem that you've seen before, which is just similar to this problem, basically. I invite you to try it both ways, just to see what you get. So develop the differential equation for the elastic curve again, just like we did before. We'll integrate it multiple times and figure it out. So let's just get started. So the first thing we did was to remove these reaction forces. Sorry, the boundaries. So we removed them. The left-hand side I removed and replaced with a reaction force RA. The right-hand side, it was clamped, but because I removed the clamp condition, that means I must have a shear force V and a moment M. So those two will show up. Now, I actually didn't do that the way I'm saying it. So I want to be careful about my words there. So I removed this reaction force, that boundary at point A, and replaced with this reaction force A, but I did a cut somewhere here randomly in between. And so that's substituted by a shear force V and a moment M, because when you cut the beam, you'll get both of them. And then this distance X, we cut it at a distance X. And so now you have to figure out for that triangle, the amount of force due to that triangular distribution is the area. The height at a distance x is W naught times x over L, and the width is x. So the area of that triangular force distribution, total force is, I'll write it for you here, equals W naught XL x over L times the length x divided by 2. That's the area of a triangle. Height times the width divided by 2 gives you the area of the triangle. And that's exactly what you see there provided to you in that circle right here. And that force is going to be located at the centroid of that triangle, which is 1/3 x. And that's exactly where it's located. Now you can take moments about d so that the shear force disappears. And when you do that, you get the moment as a function of that reaction force. Notice that reaction force is not known at this point. We don't know what it is, but we'll figure it out in a minute. And I'm not going to teach you how to calculate moments about a point in this particular course, because that should have been covered in a more basic course. But if you do have questions, please come after me after class, and then or in the discussion sessions or the office hours, they're standard or piazza. So we have multiple ways to get hold of us. We do have the differential equation of the curve for the elastic curve. So we know that moment equals this equation here, but moment is also equal to that. In this case, we found what that is. I'll integrate it twice, and when I integrate twice, I get 2 new constants. So now not only have RA as an unknown, now I have C1 and C2 that are also unknown, and we have to deal with that. But the good news is we have boundary conditions. We know that at this boundary, y is 0, the deflection is 0. And when you actually plug it in here, quickly you find that C2 is 0, very quickly, just by inspection. You also notice that the slope at this boundary, theta equals 0, must be true at x equals L. So you can find the other constant. You have now this equation here, equation 1. And then at x equals L, y equals 0. The y equals 0 at x equals L because there's no deflection at this end. So you have, that's your second equation. Now you're ready now to kind of see what you can do from there. So now you can solve for the reaction force A, and that gives you 1/10 W naught times L. Because you have these 2 equations, you're able to now solve for the unknowns of the problem. Yes. Yes. I think the question is, how do you implement the fact that theta is 0 in the equation? And the answer is that at theta equals 0, the slope, I apologize. The slope is 0 at x equals L. So you can use this equation even if you want. No, not that equation. You can use this equation. Right? Right. So since the dispersion is 0, you can see I just wrote the same equation there, here, but plugged in x equals L. Can you see that? Excellent. Very good. I used the boundary conditions to solve for the constants, and we're able to get the reaction force as a consequence for statically indeterminate beam, which is pretty cool. Now that you know C1, C2 is 0, now I know C1, now I know RA. Now just plug it into this deflection equation, and when you do, you get this equation here, and that's the deflection of the beam. You will see that for statically indeterminate problems, in this case, the deflection of the beam not only depends on the moment of inertia, it also depends on the modulus, it depends on the length of the beam, also depends on the loading, the amplitude of the load applied. And then if you want to look at the slope at x equals 0, because you're interested in knowing what that slope is, just out of curiosity, you can find the derivative of this equation, dy dx, to figure out the slope at this particular point A. And that's a very straightforward calculation. Let's go to another example, if you're okay with that. So sample number 3, I will not draw the free body diagram because I was covering in more basic class, but the moment can be calculated here, can be calculated here. You can use the same procedure we have discussed. The elastic curve equation is this one, just like what I had before. I had the EI on the right-hand side. I put it to the left-hand side, but it doesn't matter. The moment in this section of the beam is 1/2 px. I'll let you try that at home. I think you will see that very quickly when you do it at home. Again, we're not going to repeat statics work in this class because that was covered in the previous class. But I'm ready to go, so I plug in moment into this equation. And now I have this formula, which I can integrate twice. In this case, we did that. Let's see. I integrated once, actually. I was using a trick. I want to show you a trick here. I integrated once. And what you notice here is that at this spot, this very spot here, in the middle, in the very middle, I get something interesting. I get that at the very middle of this beam, the slope has to be 0. Because when the beam deforms, because it's symmetric, you expect the slope there to be 0 of that beam. So what we did here, there's many ways to solve the problem. I'm just giving you one way. And the integral was done from 0 to L/2, because that's where the moment is acting in this section. But we integrated only once and took advantage that the slope is 0. So we set that equal to 0 to get the constant of integration within. So a little trick there, knowing that the slope has to be 0 right in the center. Has to be, because when the beam deforms, you expect it to look like that. That to me makes a lot of sense. And so now you can integrate it one more, or 2 more times. And when you do that, you get this is the deflection of the beam. You know the deflection at x equals 0 is 0. So you know this deflection at x equals 0 is 0. So that's 0. And that's it. That's the deflection of the beam for this particular problem. There's many ways to solve this problem. There's not only one way, but this is one of the simplest ways, given you took advantage of symmetry. So that's another thing I am showing this problem because in industry, some problems can be actually solved by looking at half of the problem. For example, if I want to look at this Android phone drop, which I don't want to do it because I paid money for it, but let's say it drops just symmetrically, then I can just model half of it and put symmetric boundary conditions. We do this all the time with turbine wheels, which have maybe over 100 blades. You don't want to model every single blade of a turbine wheel. Maybe we can model a section of it that's repetitive, right? To save computational time. An aircraft, a lot of times an aircraft, they cut the model in half and they only look at half of the model because that's more computationally efficient. We do this for a lot of different other applications where symmetry can be very useful. So that's why I illustrate this problem, but you could have solved it without using symmetry. You can just integrate it twice, apply this boundary condition and then this boundary condition, not do it exactly how I did it, but be able to actually solve it in that way. Any other questions before I move to the next